Everyone, so I'm Arpit and I'll be talking about generalized symmetry resolved entanglement entropy in 2D CFTs, and this is a work done with my collaborators Pablo and Javier. So the idea in this paper was to compute the entanglement entropy of an interval of length L in 2D CFTs which has generalized global symmetries in it. So we all know the Cardy-Calabrese entanglement entropy result for an unitary 2D CFT with central charge C and a unique vacuum, and for a given region A of length L, the entanglement entropy reads C over 3 log L over epsilon plus subleading terms, where this epsilon is the UV cutoff and rho A is the reduced density matrix. However, this involves factorization of a Hilbert space into region A and its complement, which may not always be well defined, because of which Omori and Tachikawa use boundary safety approach to compute this quantity. And what they advocated is, in order to properly define this epsilon cutoff, you need to introduce epsilon radii disks at these entangling points, and furthermore, demanding conformal invariance, you should impose conformal invariant boundary conditions or Cardy states at these points. So it's like saying that you look at your partition function and you have conformally invariant Cardy states alpha and beta. So this is like the open string channel, and if you do an S transform, it's in this closed string channel, it's like a propagation amplitude over closed string states. So using this, one can then compute what happens when you have global symmetries in your 2D CFT, so generated by some symmetry group G. So these symmetries will be implemented by some topological line operator A, which is inserted in your spatial S1 in your CFT. And since this is a topological operator, it must end topologically at your conformally invariant boundaries alpha and beta. So in order to compute a quantity analogous to entanglement entropy with incorporating global symmetries generated by a group G, one has to have conformally invariant Cardy states alpha and beta. Furthermore, these states have to be G invariant. What do I mean by that is, if you take a group element A and you act on it with a Cardy state, then you get back the Cardy state for all group elements. So if you have this in your system, then you can compute this quantity for each irrep of G, because your Hilbert space will now decompose into irreps of this group G, and you will get a result like this, where this is the universal piece and this is a piece which is dependent on dimension of the irrep dr for the specific irrep, and mod G is the volume of the group. And this G alpha captures all boundary entropy contributions, which is an overlap between the boundary state and the vacuum, and is called the Affleck-Ludwig boundary entropy. Then the question is, what happens if you have such a line which is now non-invertible? So previously in the group like case this was invertible. What happens if you have a non-invertible line? And one such example is if you look at tricriticalizing CFT, and if you look at a subcategory of it called the Fibonacci category, and there's a W line whose fusion algebra reads W square is 1 plus W, and hence it's non-invertible. So we need two ingredients, just like the group like case. We need irreducible representations for this set of lines or a category of lines, and it turns out that these are of the form C cross D, where C and D are lines, and this was done by Tachikawa et al. And furthermore, we also need the concept of weakly symmetric Cardy states, which when acted upon by these lines gives you back the state plus something extra, and this something extra captures the non-invertibility. So with this much in mind, we get an expression like this, generalizing the Cardy formula, where we have this log piece here which captures the quantum dimension of the lines and the total quantum order. And note that for invertible lines where the quantum dimension is 1, we see equipartition of entanglement at order 1 across all the sectors.